In this last segment, we will go over regression tests, as well as correlation and Cova, for a total of 6 tests. Let's start with simple linear regression. This test determines if there is a significant relationship between two normally distributed numerical values. The predictor variable is used to try to predict the response variable. So this is when we think one variable affects another in a certain direction. Like, for example, can height predict weight in college males? To run a simple linear regression, we select F test from the test family, and then linear multiple regression, fixed model, R-squared deviation from 0. You might be saying, well, we're doing simple regression, why are we doing multiple? Well, simple linear regression is just the limit case of multiple regression. We just set the predictor variables to 1. That's why. We'll use a priori as always, and then enter the default values for alpha and power. And then, since it's simple linear regression, one predictor, we enter one predictor variable. In our example, height is the single predictor variable for weight. When we determine it with background information, we'll have to select the option from correlation coefficient and add the squared multiple correlation. So you'll square the correlation coefficient from background data you collect. Calculate and get total sample size. As always, with naive, you run the initial steps as normal and then estimate that effect size to get total sample size. Digging into our example, is there a relationship between height and weight in college males? The null is that there is no relationship, whereas the alternative is that there is some relationship, either positive or negative. So I don't have background information, but we expect the correlation to be strong because heavy people tend to be taller, or maybe tall people tend to be heavy. So we'll go with a large effect size. Hovering over effect size, we'll see that for the F squared, a large effect is 0.35. So we'll enter that in. We see that regression doesn't have tails, and we get a total sample size of 25. And again, since it's simple linear regression, we have one predictor variable. Here are two practice examples for simple linear regression, one on plant data, the other on city data. Take some time and pause this module to work these out on your own before continuing on to the answers. Looking at example 1, we're given the raw data of yield and height. We can run a regression in something like SPSS or R and get a multiple correlation coefficient, that is an R squared, of 0.459. Using that R squared, we can get an effect size of 0.085, and since it's one predictor, we get a total sample size of 12. In the second example, we don't have any information of data, so we'll guess a large effect size, since the size of the city should be strongly related to the population in the city. And we have one predictor, because it's simple, to get a total sample size of 25 cities. Let's examine multiple linear regression now. It's an extension of simple linear regression. The change is we can have more predictor variables. We can have 2 or more. And there's another change in which the interaction effects can be used. So we can look at the interaction between different predictor variables. And a good thing to note is with results, while a simple linear regression, you could plot the results with a scatter plot. Multiple linear regression typically can't be plotted because it has higher dimensions. So, taking our example from before about males' weight, we can add additional variables of age and time to that height. Do this in G-power, F-tests, again do linear multiple regression, alpha power, and whatever the number of predictors are, it will be greater than 1 now. With background information, you're going to have to enter the correlation coefficient. If you want to use from correlation coefficient, that option, you can enter a squared multiple correlation coefficient. If you have the individual predictor correlations, like from a correlation matrix, you can add those, specify the matrix, and then add the correlation coefficients from a correlation matrix to the outcome, and then accept those values. We'll look at that more in a moment here to visualize that. And can calculate the effect size to get a total sample size. Naive is the same, you just estimate the effect size rather than calculate it. Digging into that example of can height, age, and time spent at the gym predict weight in adult males? Null is it can't, the alternative is it can. So we do some trial data. This is a correlation matrix, so it looks at the correlation of each variable to each other. See the diagonal isn't really informative because these variables are perfectly correlated with each other. And the lower triangle and the upper triangle are the same. They're just either weight versus height or height versus weight. It's the same thing. And since we're only interested in the correlation of weight to these other ones, we only need the 3 highlighted values of weight compared to each of the other 3. We don't need, like, say, gym time compared to height or height compared to age, etc. So if we click determine after entering, we have 3 predictors and then our alpha and power. We can either do correlation coefficient, or here we're doing from predictor correlations. Then we specify the matrix C, which brings this up here. And then we can enter the correlation coefficient. So from here, those will come up here. And then there's 3 predictors. And then we'll accept values. And that will let us calculate and then get effect size of 0.23, which gives us a total number of 50 samples needed. Here are 2 practice for multiple linear regression. Take some time to fill these out yourself. On Berry information and, again, city. Looking at the answers for 1, we again have raw data. So we can put these in something like SPSS and get a correlation matrix. Enter those in to get a multiple correlation coefficient of 0.944, which gives us a whoppingly huge effect size. And so for 3 predictors, we only need a sample size of 6. In the second information, we have different predictor variables, but nothing else. So we'll just guess the effect size. We'll say large because these seem to be things that would predict population. We have 4 predictors: size, number of houses, number of apartments, and number of jobs. And we'll get a total sample size of 40. Moving on, we have Pearson's correlation. Now, correlation is not the same as regression. Regression implies that one thing affects another. There's a directionality to it, whereas correlation is more interested in, is there a relationship at all? not directionality. Now, Pearson's correlation in G-power can test if there's a difference actually between two correlation values themselves. So that means the categorical variable is a grouping variable that's binomial. It's better to show this with an example. So is there a correlation between our studying a test for group A? So that's the first correlation. Is it different from a correlation between test scores for group B? So two different correlation values. To do this, we would use a z-test and then correlations to independent Pearson R's. Now we have tails again, alpha and power, and then like we've seen before, allocation ratio. We can enter 1 unless the group sizes are different. If they're the same, it's 1. If we have background information, we can add those two coefficients and then calculate and transfer to get effect size and then total sample size. Otherwise, we run as above and estimate if we have no background information. Taking a look at the question, is the correlation between our studied and test score for group A statistically different than the correlation between our studied and test score for group B? Presuppose we don't have data, with the null being there is no difference in correlation, where for the alternate there is a difference. We're gonna expect or guess that the effect size is small. So for this test, if we once again hover over our effect size Q, we see that small equals 0.1 for this test. Now we're going to use two tails because we asked if it's different, not if one's greater or less than. And it spits out, since we had equal group sizes, a total sample size of 3,146, half for each of the two groups. Here are a couple examples you can take a look at yourself on height and weight in men and women, and then lab mice. For the first exercise, we have raw data, so we can plug that into SAS, get correlation coefficients for men and for women between height and weight, which gives us an effect size of 0.4. And then since these groups were the same, there's 5 in each group, 5 men, 5 women, it's a sample size of 1.0. So we need 99 per group, or 198. Now you might have noticed that the effect size spat out is negative. It's the same as if it's positive. The sign doesn't matter here. It just depends on which coefficient you entered into which box. For the second, we don't have any information other than we're asking if it's higher. So I guessed a medium effect and assumed equal group size and found that the total sample size was 282, so 141 per group. Next, we'll take a look at non-parametric regression, as opposed to simple linear or multiple linear regression, which assumes that the response variable, the y variable, is a continuous variable. Non-parametric regression does not. There are a lot of different kinds of nonlinear regression. The two we can do in G-power are Logistic and Poisson. So we'll start with Logistic. This is where the response variable, or y, is binary, like 0, 1, yes, no. It tests whether a continuous predictor, like say body mass index, can significantly predict binary outcome, like mortality, yes or no. And you can run this with or without more covariates. And you can also run this for a dichotomous predictor, which is like not continuous like body mass, but something that's non-continuous. But we're just going to show continuous here. But it's important to know you can. To do this in G-power, select z-test, then logistic regression. And then under the options button, you're going to need to set input effect size as 2 probabilities rather than odds ratio. You can add your 1 or 2 tails, your alpha, and your power. And then you're going to need to add certain probabilities under both the null and the alternative. We'll talk about that in the next slide, as well as the R squared other X box, as well as a distribution. So you have to look at your distribution of the predictor variable to do this. And then also the number of parameters, which will depend on the X distribution. So get all this done, you're going to be able to calculate effect size and then total sample size. So let's look at those parameters we need to enter in the logistic regression and how we actually get them. So the first, which is the probability of the Y variable response being 1, when the main predictor variable is 1 standard deviation above its mean. So this is based on background information, or you have to just guess. The second probability is a probability of the Y variable with a response of 1 when its main predictor is at its mean. So this is for the alternate hypothesis. Once again, you do the same thing, either get background information or make a guess. And then the third thing here is the R squared other X is the expected R squared between the main predictor variable and the other covariates. It's what it is it's the amount of variability accounted for by covariates. Now, if there's no covariates, which is the simplest case, which is what we're looking at, we're just going to enter 0. However, otherwise you have to calculate it with regression, predictor under data with other covariates. If you need to sort of guess this or just if you don't have background information, these are some naive assumptions for no background data: low, medium, and strong. Then fourth, there's the X distribution, is the distribution of the predictor variable. A lot of times, if this is normal data, that's great, unless you think that the data is distributed differently. And then for every distribution, there'll be different parameters you need to add in there. So for normal distribution, there's the mu, which is essentially it's the population mean, while sigma is the standard deviation. So a lot of times you can get that information from background data or have to estimate it. Looking at our example, does body mass index, BMI, influence mortality? We would set the null as it doesn't influence mortality, whereas alternative is it does influence it in some direction. So look at, say we had some background information, we think that this first probability is low, so at like 0.15. So at the mean, the population mean, we expect mortality to be 15% over whatever time period here. Whereas the alternative is if there's a standard deviation difference, it's going to be higher. Now so we have those, we can fill those out. Now since we know that we have only one predictor, this can be 0. And body mass index seems to be normally distributed, so we'll set that at normal and then have it based around a mean of 0 and a standard deviation of 1, which is standardized. And we're going to do cares because we don't really care about the difference. And then making sure, of course, we go to options, which will pop this up, and use the 2 probabilities to be able to get the fact that there's these probabilities here. This generates a sample size of 158. So before we do any practice, let's look at our other non-parametric regression we can do, which is Poisson. This is different from Logistic, in which Poisson, the response variable is a rate. It tests whether a continuous predictor variable influences the rate of events over a set period, With covariates, again, you can use dichotomous, but we'll just show continuous predictor variable. Sometimes Poisson distributions are better or more clear explained as like count data, like counts over a certain amount of time, as opposed to rate. Now, it's important to know that Poisson regression assumes independence of observation, so one count won't affect another one. So subjects can have multiple events as long as they are independent. Example of, say, a Poisson sort of question would be, does a change in drug dose decrease the rate of adverse effects? To do this in G-power, we will select Poisson regression from the statistical test, not logistic, and this will be under the z-tests. Again, we'll do tail, power, and alpha. You also need to do this expected beta 1, as well as base rate expected beta, or exponential beta. We'll explain that in just a second here. And then means exposure, I'll explain again. Just like in logistic, we can have the r squared other x. It's going to be 0 for the simplest case of no covariates. And we'll have to select distribution and parameters like we did for logistic. So let's take a look at total sample size. Sorry, this calculates total sample size. Let's take a look at those parameters. So for Poisson, we have more parameters. This first one is the change in the response rate with a 1% increase in the predictor variable. So for example, if we expect the response rates to go up for 20% per 1 unit predictor increase, this value would be 1.25. It's 25% over 1. If we expect to go down by 30%, it's going to be 0.7. So this is essentially the change because of the effect. Whereas the base rate is if there is no intervention, there is no treatment or whatever you're testing. So you need to know what your unit of exposure is and what rate is counted. So from that unit of exposure, you can get the base rate. So that's the number of events expected per length of exposure. So an example, if a base rate of like having 13 events per 30 days, so like maybe you have 13 headaches over 30 days, you have a base rate of 0.43, or maybe you're looking over miles of how many clouds you see per 20 miles driven, base rate of 0.05, etc. You know, number of events with the number of volunteers. And then there's the mean exposure, which is how long the length of exposure of whatever the study is going to last in terms of units of exposure. So these are, you have to know the unit of exposure as well. Once again, the r squared other x, the x distribution, and the x parameter boxes are calculated the same way or estimated the same way as in logistic. So here's an example for a non-parametric Poisson. Does a change in drug dose decrease the rate of adverse effects? Null is there is no change in adverse effects with drug dose change, and the alternative there is. So say I don't know background information, I could sort of try to guess things. So maybe I expect a moderate decrease in rate with an increase in drug dose. So maybe like 0.20 or 20%. That will set the this value to 0.80. So let's do a unit of exposure as in days, and events will be adverse effects. So let's say the base rate will be 1 adverse effect per day, which is 1. And let's try this for a month, so 30 days of mean exposure. So base rate of 1, mean exposure of 30. We expect a change in drug dose, or we expect a decrease in negative effects based on drug dose change. We have no other predictors, so that will be 0. And say we have no idea the rate of adverse effects distribution. Let's just go with uniform, and then take one tail because we're interested in decrease in rate. And with uniform, standard would be 0 and 1. We find, putting this all in, a total sample size of 98. So you can take a moment here to pause this and practice some non-parametric regression. Okay, for the first one, we have raw data, and this looks like logistic regression because we see that sleep disorder is binary, no and yes, while temperature is a continuous predictor variable. And since, let's see here, we don't see a directionality, we use two tails. We can get means for the temperature and standard deviation to get essentially a one standard deviation range. This is the low and the high end. So then the probability under the null is going to be 0.33 because we only had one sleep disorder. It ranges outside one standard deviation. And then that makes the other probability to be 0.67. Since we have no other covariates, r squared 0. Temperature should be normally distributed, so I standardized it to get a total sample size of 195. For the second one, we have no information, but I see the word rate, so that makes me think it's Poisson. And there's no directionality, so we use two tails. Given that there's no background information, I'm going to expect a small unit increase in lung cancer incidence changes with an environmental factor, so 2% per every unit increase. And just taking a little bit of like rate of cancer just in general, found a rate to be 57.8 per 100,000. And since we're doing 3 years, the mean exposures will be 3. And again, r squared 0 because we have no covariates. And we'll try a normal distribution standardized to get a total sample size of 116. All right, we'll round this out with an Cova, which is a blend of ANOVA and regression. So it tests whether the mean of a dependent variable are equal across lengths of a categorical independent variable, often called a treatment, while statistically controlling for the effects of other continuous variables that you're not interested in, also known as covariates. So an example would be, is there a difference in recovery time across 2 conditions and 3 diagnostic groups with baseline scores as the covariate? So this is the continuous variable, and we're not interested in it, but we want to control for it. So that's the regression part of it. Whereas these ideas of 2 conditions, that's categorical, 3 diagnostic groups, that's also categorical, that is where we get the ANOVA part of it. To do this in G-power, it's an F test and Cova. We will need to do alpha and power like always, and then numerator degrees in freedom and number of groups, same way as we did with the multi-way ANOVA. And since now we have covariates, you'll have to enter the number of covariates based on your design. To get effect size, with background information, we'll need to get a partial data squared as this, like we did it in the ANOVA, or guess if we're naive. So turning to our example, is there a difference in recovery time across 2 conditions and 3 diagnostic groups with a baseline score as a covariate? Null being there is no difference. Alternative means there is a difference. I don't have background information, but I expect a medium effect, and hovering over effect size F here tells me that for ANCOVA, the medium effect is 0.25, so I'll enter that here. Now, the numerator degrees of freedom is going to be our degrees of freedom of our two conditions, so that's 2 minus 1, which is 1, times our three diagnostic groups, which is 3 minus 2, which is 2, which equals 2. And of course, our number of groups is 6, because that's 2 times 3, 2 times 3. And then there's one covariate, which is the baseline score, so we'll add one covariate here. And what we find is we need 158 samples total. Here's 2 practice ANCOVA on weight loss and another weight loss. For the results, we see that we have the raw data here, and there is going to be treatment as the effect we're interested in. So the numerator degrees of freedom is going to be 3 because there's 3 groups, drop X, Y, and Z. Minus 1 equals 2. And we want to control for body weight. So 3 groups, 3 treatments, and then 1 covariate. Now, we can put this raw data in a general linear model in SPSS to get our sums of squares, to get a partial eta squared of 0.213, which gives us an effect size of 0.52 and a total sample size of 39. For the second one, we're giving no information other than we have a diet style, our groups, so our degrees of freedom is 3, 4 minus 1, and we want to control for starting body weight and height, so we have actually 4 groups for 4 diet styles and 2 covariates, weight and height. So guessing a medium effect size gives us a total sample size of 179. So, in kind of conclusion here, I'm going to bring up what is called a generalized linear mixed model, kind of as a postlude. So this GLMM, which is often how it's abbreviated, is the most expansive model for statistical analysis and what a lot of the field would be doing. You can use fixed effects, random effects, categorical predictor, numerical predictor, and a variety of distributions, not just normal. It's kind of the one-stop shop, general purpose, sophisticated, you name it. So we could answer questions like, can height, weight, rate of driving speed, gender, age, ethnicity, and number of weekly drinks predict the probability of car crashes? And the probability of car crashes are non-normally distributed. So unfortunately, with G-power, GLLMs are beyond the scope of G-power's ability. But they are kind of where the field of statistics is at, so it's important to know how to use them and get sample size. So please stay tuned for other approaches in software, such as R, SAS, and Excel, where we'll hopefully be able to take into account GLMMs. Then, as a note, turning towards clinical study designs for important understanding of taking what we've talked about here and applying to specific studies. Here's just a short table. On the left here is some common study designs like randomized controlled trial, double-blind, cohort, case control, and cross-sectional. Just a bit of a description, and then what typically are used. So ANOVA we see pretty common, and as well as regression. So the ANOVA and regression examples we looked at are helpful for all these common study designs. So finally, I want to thank you for walking through these module sections with me. Again, this was put on and supported by DaCCoTA, and which is supported by the National Institute of General Medical Sciences of the National Institutes of Health. And so please, if you use this in any way, please acknowledge us in publications. You can say simply, research reporting this publication was supported by DaCCoTA, the National Institute of General Medicine Sciences under the National Institute of Health under award number, so forth. Thank you for your time, and I hope this was helpful for your experimental design and sample size calculation needs.